The hypervisor can allow the guest OS to make changes to the guest status CU2 field without intervention from the hypervisor if the SFC2 field is set. Otherwise, a change to the guest status CU2 field will result in a field change exception to the hypervisor. The CU2 field controls the access to coprocessor 2, and a guest OS may want to limit the access to one user process at a time. So when a guest user process causes a coprocessor 2 unusable exception, the guest OS will need to do a context switch of the coprocessor 2 registers. The security policy may find this acceptable and allow this without intervention from the hypervisor by setting the bit. The hypervisor can also allow the guest OS to make changes to the guest status CU1 field without intervention from the hypervisor if the SFC1 field is set. The CU1 field controls access to coprocessor 1, which by convention is the FPU, and the guest OS may want to limit access to one user process at a time. So when a guest user process causes a coprocessor 1 unusable exception, the guest OS will need to do a context switch of the FPU registers. The security policy may find this acceptable and allow this without intervention from the hypervisor by setting the SFC1 bit. The guest control 1 register contains 3 IDs. EID is the external guest ID set by the external interrupt controller when an interrupt is raised for a non-resident guest. This is used to determine which guest the interrupt is for. The hypervisor can check the EID against the ID to determine if the guest currently resident is the guest the interrupt is intended for. If it isn't, the hypervisor should swap in the intended guest. This was covered in detail in the interrupt section. RID is used when the guest control DRG field is set and the hypervisor is performing TLB operations that are targeted to a specific guest ID given by the RID field and not the root TLB entries. ID is the ID of the current resident guest set by the hypervisor when the guest is swapped in. The meaning of the fields in the guest control 2 register depend on the interrupt mode. If the core is in vectored interrupt mode and not external interrupt controller mode, this register is used by the hypervisor to send an interrupt to a guest OS. The hypervisor will receive an external interrupt if it is interrupted for the guest that is not resident. It would then switch in the intended guest context. Setting the associated hardware clear in the root guest control 2 HC field will cause the associated interrupt pending bit in the root cause IP field register to be cleared when the bit in the guest cause IP field is deasserted. This field may be hardwired as a read-only bit set to 1 or 0. Setting the associated virtual interrupt pending bit in the guest control 2 VIP field asserts the interrupt in the guest once an ERET is done in the hypervisor interrupt handler. If the core is in external interrupt controller mode, these fields are written only when an interrupt is received on the root interrupt bus for a non-resident guest. The external interrupt controller writes the following fields: GRIPL is the requested interrupt priority level. In the MIPS EIC implementation, this is treated as the vector number for the processor once it enters guest mode. GEICSS is the external interrupt controller shadow set number. The GVEC is the guest vector offset that would be provided by the EIC, which would be used directly as the interrupt vector once the processor enters guest mode. Note, this is not used in the MIPS EIC implementation. The GRIPL, as described previously, is used as the vector instead. Guest lowest shadow set number determines the lowest physical shadow set number associated by the route to the guest. The guest SRS control HSS field is the highest number shadow set for the guest in the guest context. The guest is thus assigned the physical shadow set range between GLSS and GLSS plus the guest HSS field. Note, the guest lowest shadow set is the set the guest will use for its GPRs. If you have a shadow set, it's a good idea to assign at least one for each guest so that when the processor switches to root mode or when you context switch out a guest, you will not have to save the GPRs. Guest Control 0 EXT is an optional extension to the Guest Control 0 register. It adds additional control features to the virtualization module. The Guest Control 0 G0E field should be read to determine if there is a Guest Control EXT implemented. CGI allows the execution of cache index invalidate operations in guest mode. If the Guest Control 0 CG field is set to 1 and the Guest Control 0 EXT CGI field is set to 1, then all cache and cache E index invalidate operations may execute in guest mode without causing a guest privilege sensitive instruction. FCD disables guest software hardware field change exceptions. OG adds the guest CP0 registers user local, WRENA, user trace data 1, user trace data 2, K-scratch 1 through K-scratch 6 to a list of registers that will cause a guest privilege sensitive instruction exception. BG bad register GPSI enable adds guest CP0 registers bad vadder, bad instruction P to the list of registers that will cause a guest privilege sensitive exception. MG adds the guest CP0 registers index, random, entry low 0, entry low 1, context config, page mask, and entry high to the set of registers access that will cause a guest privilege sensitive instruction. The guest count register is always relative to the root count register. The GTO offset register is used to offset the root count register. The result can be read from the guest count register. Any writes to the guest count register always result in a guest privilege sensitive instruction exception, so the hypervisor can make the proper adjustment and write to the GTO offset. Here is what happens when a guest OS tries to set its count register. When the guest OS executes an MTC0 to write to its count register, a guest privilege sensitive instruction exception is raised, giving control to the hypervisor. The hypervisor decodes the instruction. The hypervisor calculates a 2's complement of the current value of the root count register. Then it adds the value to the guest setting, and it moves the results to the GTO offset register. Then it calculates the new PC for the guest to continue execution from by adding 4 to the bad instruction pointer and moving that value to the EPC register. After the hazard barrier instruction is executed to make sure that the write of the GTO offset register has taken effect, it executes an exception return instruction. The guest OS continues execution none the wiser. Here is a diagram of a timer interrupt in the guest and root context, assuming that the root count register is a hex value 42 to start. Let's assume to set up the timer, the guest will zero out its count register, so the GTO offset will be set to a negative 42. The guest will set its compare register to hex 100. And the root sets its compare register to hex 200 at the same time. Each cycle, the root count register will increment, which has the effect of incrementing the guest count. 100 cycles later, the guest count will be 100, equaling the guest compare register, and the guest OS will take an interrupt. 100 cycles after that, the root count will equal the root compare register, and the hypervisor will get a timer interrupt. There is a new code for the root cause exception field to indicate a guest exit or GE. The hypervisor exception routine will decode the exception code field and find it is a GE. It would then decode the guest exception code to further refine which exception it is. The root config register has a new field called VZ, which when set indicates that the virtualization module is implemented for the processor. There are 2 new instructions to move from and to a guest set of CP0 registers to a general purpose register. The guest CP0 context is somewhat configurable by root, in that it can be a subset of the root context. Some of the fields in the configuration registers of the guest context that are normally read-only can be deconfigured by the hypervisor. The intent is for the hypervisor to do this deconfiguration before starting the guest code and not to change it once the guest has started. The virtualization module architecture allows for many of the guest configurations to have writable fields. The actual core implementations limit the root writable fields to the list shown here. This ends the virtualization module section.